Here.
Wonderful, thank you. Can people in the chat just confirm that they can hear us?
Yes, I can hear you.
Okay, wonderful. Okay. Okay, well, we should probably start. So welcome to the fourth and last workshop of this eye tracking series before we actually start the practicals in person, starting with the 22nd of February, I believe. So I hope to see some of the people in the room and perhaps some of the people online if you want to take part. The people online come to Warsaw if you want. We will give some information about that towards the end. Now, before we start with today's presentation, I just wanted to point out that this is not going to be a statistics class. Okay, so actually, some of you might have noticed that we have amended the title to be a bit more inclusive, right? So it now says data handling and data analysis. So if you were thinking that you would get a crash course in statistics, I'm sorry to disappoint you. What you will get is an in-depth look at all eye tracking data issues and operations that you need to perform the moment you stop collecting the data. So you have the data is still in the software. What do you need to do before you get to the data analysis? So let's have a look at the content for today. So first, Agnieszka will talk about data handling software. We will concentrate on Data Viewer for iLink and BGaze for SMI, primarily because these are the two systems that we will look at in the practical sessions that are coming up. So Agnieszka will talk about viewing sessions, interest area, interest periods, and then I will be taking over and discuss data quality and possible exclusions that you will have to make due to data quality issues. We'll talk about manual inspections, calibration checks, drift correction, just amongst others. Then I'll also discuss data cleaning, which is a separate procedure to exclusions due to data quality. So we'll look at fixation trimming, merging, and outlier removal. Then I'll pass on the baton to Agnieszka to talk about data export. So this is very exciting. You know, once you've done all your cleaning, well, you can get the data out and finally see what it looks like and run some analysis. So in some distorted way, it probably is quite exciting, right, to see it there. So Agnieszka will talk about report types, which is linked to analysis. And then we will both be talking about data analysis. So I'll stress the importance and the length of pre-processing, so the amount of operations that you need to perform on these data sets before they're ready for analysis. And then the usual suspects, normality, the importance of visualizations. Then Agnieszka will talk about ANOVA's t-tests versus linear mixed models. And then if there is time, I'll say a little bit more about fixed and random effects. So the reason why mixed models are called mixed, right? If there is time. So lots to cover. So let me just pass the floor to Agnieszka to talk about
That's right. Thank
the
you.
software.
Okay, this is exciting actually. I'm not sure about the experts, but let's get started. So the idea is we've collected our data and the special software for this, and each manufacturer has special software. And normally what happens, there's one piece of software for data collection and another piece of software from the same manufacturer, which you can or you don't need to use if you have some better programs. And then you move on to actually before you analyze to define what you want to focus on. So in our case, in the iLink system, the data analysis and the processing and export software is called the Data Viewer. We will look at Experiment Builder when we'll in the practical in a hands-on session. Today it's Data Viewer. For the SMI, analogically, it's actually called BGaze. So we'll be referring, as Valentina said, to those things. Here's a screenshot of a viewing session in iLink. So when you work with iLink, what happens, when you want to analyze something, you create what is called a viewing session. Then you import your data and you perform some operations on it. What's important is to remember that you don't actually work on the raw data, but what you do in your viewing session doesn't in any way affect the original data, which is good news if you do something stupid, which sometimes happens. Is there anything you want to say in particular? No. Okay, we'll be looking into this in the spring, I think. All right, so we've got those viewing sessions in iLink, and what exactly do you need to do? First thing you do, of course, you need to load your files. So all the participants and all the trials that you want to analyze, then you create areas of interest, and in some systems you also create interest periods. I'll explain that in a moment. Then you do a little bit of processing. We'll be talking about that in a moment. You can visualize the data. This is the most exciting part that everybody gets excited about. So all those things that we already mentioned, like scan paths and heat maps, etc. And most importantly, this is where you export the data. And we'll show you this. So when you talk about eye tracking, and we mentioned that already in previous sessions, you need to define what exactly you want to analyze. So if you're showing viewers a picture, if you're giving them a text to read, if you're giving them a video, what you can do is you can export all the data from all your stimuli, but it doesn't make sense because you're probably interested in some particular time or some particular geographical, so to say, area on your screen. Okay, so this area on the screen that you're interested in is referred to as area of interest and AOI. Some people say region of interest. So you'll have different terms for this. But essentially it means, and it could be measured like in pixels on the screen, where on the screen you want the data to come from. Okay, we'll be showing some examples. So where? In SMI, that's it. But in iLink, it gets more complicated because we also need to define interest periods. So not only do you decide the area of the screen that you want to analyze, but you actually specify the duration of the time that you're interested in, okay? For us, for instance, when we analyze the reading of subtitles, we are only looking at the time periods where subtitles were actually displayed and not at some other moments when they were not on the screen. Okay, so with interest periods, the main question is when your data will be collected, and it's yes, that's it. Yes.
So there's a bit of manual processing to do with that. Yes, yeah. And you use messages to create those. So these messages are inbuilt, and so they're already there, and they're used to communicate between the iLink, between the display PC and the host PC, and then you use these messages to define. So subtitle appears, subtitle disappears, and this is going to be the two in time and out time of your interest period.
And we're lucky enough to be able to use the data from subtitles. So we have the time codes, and we simply coordinate that. Okay, I guess roughly speaking, that's it. We have a lot to say, so I can't really dwell a lot on these things. Now, in terms of interest areas, there are two types: static interest areas and dynamic. So for static areas of interest will be those that actually don't move. So for stimuli such as a picture or a text that the participant reads, okay? The moment you define area of interest, it's there typically for the whole duration of when the trial was displayed, this text or this picture was displayed, okay? For dynamic areas of interest is for stimuli that change in time. So for instance, well, the video would be an excellent example of this, okay? A couple of examples. So these are examples from the SMI software. You have two texts, and what SMI can do if you're analyzing text, it can automatically divide this text into a separate paragraph. I think that's the green thing, into separate words. These are the yellow dividers. The purple ones would be sentences, and it can also do separate characters, okay? And that's very simple. It's done automatically on text, not on subtitles, as I mentioned earlier. And these are static areas of interest, right? It's just defined, and they are there for as long as a person reads. You remember this picture from our first talk, hopefully. So areas of interest don't need to be words. If you're doing other studies, such as images here, you yourself define the areas using the area of interest editor. So there are different options. It could be a circle, could be a rectangle, okay? And here you decide, okay, I want an area of interest on the baby, on the text, on the picture, etc. Right? So it's up to you. And once you do that, the exports, the data that you will be exported, will be based on these areas of interest. So you define first what you want, and then you export, and then you'll have the data grouped based on the areas of interest that you defined at this early stage. Stop me if you have any questions at any time.
Can I have a question? So I think I had a totally wrong idea that you have to define all the areas of interest before you actually run the experiment.
You don't need to. You don't need to. Sometimes if you know, for instance, that you're interested in like multi-word expressions, right? You can be clever. We weren't clever in our previous experiment. We weren't clever enough. Yes.
Expressions,
So you can actually tell the software before, you can mark these, and they will be marked later with messages, I think, right? Let's not get into that maybe at this stage, but you can do that. But with areas of interest, you can do it later. No,
maybe I'll just say, so I don't know if you remember, but from one of those early workshops with Marcus, there we used, so if in the text you're interested in every word, then this is done automatically because the software uses the space between words, right? Now with multi-word expressions, how do you know that these 3 words are to be grouped together? The eye tracker doesn't know, right? So then that's when you do a little bit of clever processing that Agnieszka mentioned by, for example, using asterisks. So in the early process in Experiment Builder, so this is some pre-processing that you need to do, right? If you're interested just in all the words in a text because you have other categories already, for example, you already know that some words will be cognates and some will be non-cognates, then you don't need to do any pre-processing and the areas of interest will be created automatically.
Mm-hmm. Yeah, so just to make sure, you can do them before, you can do them during data collection because it's different piece of software, right? So an experiment will be maybe running and you're doing areas of interest on a different laptop, let's say, or after. It's it doesn't matter really. It's just you need to do this before exporting the data. That's crucial because this is where the data comes from. I said there are some standard shapes, but you can also define a shape that you need for your particular stimuli. As you have here, you've got these areas of interest drawn with this freehand option tool. So it's really flexible. Whatever you need, you can have. Okay, some more examples, area of interest on subtitles. This is with SMI where we have to draw everything manually, including single words. So we don't use this system now to study reading with subtitles. You can have those areas of interest, not word-based, but you can have an entire subtitle or the video. Again, depends what you're interested in, what you want to find out. There are different options. And this is a window from iLink where you define interest periods. It's basically, you need to say for each interest period when it starts, and it can be based on some messages or time periods, etc. Do you want to add something?
I think you can just see there. I don't know if you can see the cursor, but you see message text here. So EDF message you can use. And you say basically here would be the in time. So IP starts, the start of the IP, and this is the end of the IP, right? So you use these messages quite a lot to mark. You can make comments and these kind of things as well. I think that's all that I wanted to add.
Yeah. Mm-hmm.
Okay, so I'll then take over a little bit with talking about data quality. Now, the first thing I would like to say here is start with a quote, right, about the very first thing that you might want to do, which is manual inspection of your data. Like we can maybe move this so that people can read the quotes. So manual inspection of scan paths. So checking data quality is undoubtedly the most common use of scan path visualizations, despite being informal and undocumented, right? So of course you will be doing this. Just be aware that it is only one way of assessing data quality. Now, first of all, also, what do we mean by scan path? So what is a scan path? This is multiple scan paths, in fact, as indicated by colors. And here, the data quality is pretty good across all of them. Here, instead, we have another examples where particularly the red scan path, right? So this is 2 participants. The participants represented by the red color, as you can see, for this participant, the data isn't as accurate, right? So we can see what we call drift, right? So an offset, so the gaze is not exactly where we expect it to be, is a little bit out, right? In this case, it is lower. So this is what I mean by manual inspection. You can basically replay your recording. In our case, is video with subtitles, and you can look with the gaze overlaid. So in this case, on the subtitles, and you can diagnose some potential issues. So manual inspection is a powerful diagnostic tool. However, it is rather time consuming. Let's say that you have 70 participants, 3 trials per participant, 3 videos, and each video is 7 minutes long. Well, that's 20 minutes per participant times 70. That's quite a long time, right? And also it is an informal way of looking at the data, something that you will certainly do. So I wanted to mention it first. However, we would recommend that you apply this to a subset of recordings, right? Because it's so time consuming. So, and then the natural... Well, this depends, right? So the next question will be, how do you know which recordings need to be further inspected? Well, I will look into very many different ways that you can use, starting from the next slides. However, the main thing that I'd like to point out straight away is make some notes during data collection. Just as a reminder, at least in iLink, you have 2 PCs. You have the display PC where the participant is sitting, and then you have the host PC. So you are there, and you can check data quality live as the experiment unfolds, particularly with iLink, because you can see at all times pictures of the eyes, right? So, and you can see where the participant is looking. So rather than just sitting there idle on your phone or something like this,
areas of interest.
Or do areas of interest, do keep an eye on that participant that you're testing. We have a spreadsheet and we routinely do this so that, you know, if for whatever reason the participant moves or they fall asleep or whatever, and so the gaze totally disappears for a sizable amount of time, make a note, participant code, number of the trial, and perhaps at which point in the trial, right? And if you are logging this, because you will not remember once you get to participant number 20, it's all going to be, you know, lost. If you make notes of this, then you already have a pretty clear idea of which participants may be problematic and which participants you may want to go back and inspect manually, right? So this seems like a quite obvious thing to say, but it would be surprised how many people don't do this. And we find it works pretty well to know where to concentrate your efforts. Okay, so this is the first thing. Then the second thing, obviously, if you see drift after manual inspection, you can correct for this. So in data...
The blue and red.
It's the red, yes. So the blue was kind of, well, I guess it's still okay.
Yeah.
But
so you can see they're definitely reading, okay, but their gaze is not on your any areas of interest,
Yes.
or some of it.
Yeah.
Mhm.
And actually in this case particularly, there's a black you know, bar at the bottom. And so it's unlikely that the participants were just staring at black, right? It's quite likely that they were just reading the subtitles, but the gaze is just too low, right? So this is how inaccurate. So that's the drift there. So this drift can be corrected in Data Viewer. You can do this via single point adjustment, and batch drift correct is another feature that we have started using recently. In SMI, in BGaze, you can also do that. And in Tobii Pro Studio, as far as I am aware, you cannot do that unless things have changed recently. Possibly one of the very few things I actually agree with Tobii on doing. I am not a fan at all of this. I know Agnieszka doesn't agree, so I won't dwell too much on it. But it is basically fiddling with the data, so please do not unnecessarily fiddle with it. You can do it, right? However, especially if you use the batch drift correct, right? You have a full recording, and you will apply this offset. So you take the whole data and you turn it and you shift it down or up by a certain amount. Now, let's suppose that a video is 7 minutes long, right? What would justify doing this is that if this drift was substantial and if this drift was consistent. So let's suppose that, you know, for the first half of the clip, the participant is okay, right? And then something happens, they adjust themselves on the chair, and all of a sudden your data is out. Well, if you apply this batch drift correct, then you correct the second half of the clip, but then the first half will be out, right? So it's always a judgment call. It is basically fiddling with your data. I recommend against it. I take the liberty to say that. But, you know, we have... yeah.
Yes.
You can in BGaze, and I think you can. I'm not sure if you can in iLink. I refuse to do it because I think it's fiddling with the data. I don't like it. I think, you know, as we say in Italian, prevenire is meglio che curare. So if you want to prevent something from happening, it's better than have to cure it later, right? So ensure that data quality is good by doing a host of things that we talked about in the previous sessions, right? Obviously, this this would be already the data that's being pre-processed into fixations, right? Yes. So, I mean, but I'll show you actually a case in which it is warranted to do that because the drift was substantial and was consistent throughout the trial. So on the left, you can see this is one participant where you can see clearly that both lines are being read, right, in the subtitle. So you have
These are aggregated areas of interest. So all
yes.
the subtitles for this.
And it's like a view for one participant with all of their fixations on the image and on the subtitles. And you can see that you know, on the image on the left, both lines were looked at. However, in the screenshot on the right-hand side, you can see clearly that what looks like the first line is actually the second line, and gaze on the first line is actually out of the interest area, right? If we look here. So in this case, after manual inspection, so you have to make sure that you watch the whole clip in this case, which makes it quite time consuming to assess, right? Then actually implementing the offset is not a big problem, right? It's very quick, but it's gauging, it's assessing which recordings may need it. That might take a long time. However, in this case, you know, we have some cases in which it was worthwhile doing it. It was beneficial. Yes, yeah. So
question.
Good question. The first one is what extent we can really manually hold fixation. Because I had an experience when only the initial fixation of the line was drifted down, but another fixation.
No, you wouldn't move single fixation.
Well, there is an option, yes, single fixation, but this is what I mean. You know, you start fiddling with the data. It's like, okay, well, this is out, this is not out. I mean, I personally don't like it.
No, here, like when it's obvious, right, and it happens consistently, right? You wouldn't manipulate one fixation for any reason. Oh.
Yeah, and you said you have two questions.
Yeah, the second question was, do we actually can move one particular?
You can, yes, in iLink you can.
But would you want to? Probably not.
Yes, it is totally, yeah. So I would even try to not say that this option exists so that people don't feel tempted, to be honest. And I don't know, you know, if you implement your data quality procedures, you won't need to do that. Most of your recordings are going to be usable as they are. So tracking loss, so we talked about manual inspection and correcting for drift. Tracking loss is another very important part of data quality assessment. It usually includes genuine blinks, right? So whenever the data is lost, whenever there's no eyes recorded is when we blink, of course. However, blinks are regular and they're really short, so they are quite and they affect everyone needs to blink, so it is relatively easy to gauge whether, you know, there are other further problems there. For example, if someone is falling asleep. Tracking loss can be assessed via manual inspection, but there are better methods. So in Data Viewer, you can actually export a specific type of report called a trial report. Agnieszka will talk about that later. And so you can assess tracking loss precisely. You can give you can assess it numerically, let's say. And then you will have to choose a threshold, and generally we exclude trials where the eye was lost above 10% of the recording time. However, please bear in mind, this is again a judgment call and a decision that you make. There is no sort of agreed upon threshold in the literature, and it does remain a subjective process, and it might depend on your experimental design, right? If your areas of interest are really large, or if your areas of interest are minute, and the type of experiment. So check publications in your field. I will repeat this a number of times, you know, to see what is the best practice out there already. Calibration quality is then the last important element of data quality that we assess when deciding what trials or what participants to include or exclude. Obviously, we've talked about calibration quite a lot in the previous sessions. If a model is suboptimal, this can lead to data quality issues during the recording, okay? Yes, as well, for example, drift. And so by checking the calibration values for each participant, which you can do fairly easily in iLink, this can be very helpful to diagnose potential problematic trials. However, I'd like to point out that calibration is just the initial model, right? So it's also equally possible that your participant calibrates wonderfully, they have no eye condition, and it's all great, and then halfway through the experiment, they fall asleep because they're tired, okay? So this wouldn't, you know, the fact that you have a good calibration model is a conditio sine qua non. So it's a prerequisite, but it doesn't assure that you will get good data quality, right? So that's why we also look at things like tracking loss during the recording, right? The two things are complementary. So one way to make sure that you don't have these kind of issues is to introduce opportunities for recalibration, right? So always, or at least a spot check, right? A drift check, not a drift correction, during the experiment. So typically in between the trials. Yes, so when the person finishes, they stay there, and you will have a one dot calibration, it's called, but it's not really a calibration, it's just, you know, and if the participant is out by more than a certain amount of degrees of the visual angle, the system will not let you proceed with the next trial. It will force you to recalibrate. And then the actual recommendation from iLink that we use, so we tend to retain and to consider good calibration models, those that have an average error of under 0.5 degrees of the visual angle, and the maximum error, so one-off error, as long as that's also under 1 degree of the visual angle. So that's what we use. Yes. Right, and it tells you, it even gives you a green, so there's like green, red, and orange, and it even tells you good, average, and bad, or something like this, right? So it's color-coded, and there's words, but the numbers are the most important thing, right? Because sometimes the system is quite, sometimes the system gauges as good, even something that is above 1. We're a bit stricter than that. So anything that is above 1, we flag it maximum, obviously, we flag it as worthy of further inspection, okay? So overall, use a combination of methods when assessing data quality, if possible. SMI has something called tracking ratio. Tobii has sampling rate. This is a rather coarse measure of confidence that the eye tracker has in whether, you know, it has identified the eye position correctly. Validity codes in Tobii are more or less the same thing. 0 means, so these are assigned to every fixation, and 0 means the eye tracker is confident that the eye was where the eye tracker think it was, and 4 means really low confidence, or even the eye was lost for that particular part of the recording. However, these are, as I said, coarse and inexact measures, and they are sort of one size fits all kind of measurements, right? So which we used to use. I used one in my PhD with SMI, I think, also, but I actually, it's telling that iLink doesn't have such thing at all.
But
so
we calculated.
yes, what we do is we use a multi-step approach based on calibration checks, tracking loss, lab notes, and manual inspection. Okay, so it's quite a long process. So again, check publications in your field, follow the best practice guidelines that you see there, and please, please, please always include this kind of information somewhere in your paper. You don't always see that in the publications. Let's try to change this, even if it's a matter of putting it in the appendix, because I know that sometimes, you know, word limitations for these articles between 6,000 and 8,000 words typically might make it hard to include this information, but let's always try to include it somewhere, appendices or data analysis files, for example. Now, as far as cleaning the data is concerned, this is an operation that is a little bit different. So even if your data quality is perfect, which is highly unlikely to be the case, you always are going to have to at least assess some participants, but let's assume that your data is perfect. Even so, you will have to clean the data. What does that mean? Basically, this refers to cleaning fixations. And there are 3 main methods to do so: temporal cutoffs, merging, and outlier removal. Now, this researcher, Eskenazi, recently published a review where he looked at 192 papers, so quite a lot, quite a substantial amount, published over the course of 5 years, 2018 to 2022, so recent. And he found that this is where the percentages come from. He found that 81% of, so the vast majority of papers used temporal cutoffs, right? So we'll see each of these in turn. So this basically means trimming fixations. So we typically exclude anything that is below 60 to 80 milliseconds, and we typically exclude also anything that is above 800 of 1000 milliseconds. And the rationale for doing that is that, at least for the minimum threshold, it is unlikely that any meaningful information can be extracted from these very, very brief fixations, right? As for the maximum threshold, I think it's a little bit less obvious. And the counter argument, so if we wanted to include those fixation, would be, you know, how can you be sure that this increased time that doesn't fit with your you know, data shapes and messes up your analysis, and as this then might come up as outliers, but how can you be sure that these aren't reflective of real cognitive?
Yeah, but I think most of the time the idea is that people just stare
and sort of
thinking something
yes,
else,
that's
right? So you have like 5 seconds fixation, right?
I mean, but 5 seconds isn't 1,000. That is 1 second, right? This is my
so
problem with it. But anyway,
arbitrary,
yes, it's an arbitrary, and I don't necessarily always agree with the rationale. I don't see the rationale as clear as the rationale for the minimum threshold, right? But you know, this is what the field does. So if you find a great rationale, please send it our way. And then the second option is merging fixations. Okay, so this means basically consolidating adjacent fixations that are quite small and that are very and they are quite close together in space, right? Typically less than 1 degree of the visual angle apart. It is often performed by the system automatically. However, in iLink, which is the screenshot you can see here on the right, you can have a 3 or 4 stage cleaning method. This, however, applies for reading studies for the most part, so we don't really necessarily use it. We untick stage 1, stage 2, stage 3, and we perform only stage 4, which is basically the trimming that we talked about in the previous slide. So you do both in the same kind of option. Obviously, here we would have 80 milliseconds as the minimum and 800 or 1000 as the maximum, right? And then the last way, yes, you may or may not tick that. I mean, we use interest periods and interest areas, so we don't. So this depends, right? Because if you want to look at for example, how much people are distracted, then you might want to include, right, fixations that aren't on your interest areas, right? So it really depends. We generally don't tick that. We don't delete any fixations.
There's no reason to delete, right? You're just not looking into them
because
anyway.
you're already, you know, the fact that you have interest periods and interest areas, so spatial and timing information within which only to collect data, that's already enough generally. And so the last way of cleaning your fixations is outlier removal. There are 3 ways of doing this: mean and standard deviation cutoffs, model fitted residuals cutoff. So you first fit your models, your statistical, for example, regression models, and then you plot the residuals and you look and you choose this to see what kind of data to remove as outlier, which data points, sorry. Or you can also use percentile distribution cutoff. Now, however, the very first, so mean and standard deviation cutoffs are by far the most commonly applied method, and generally most papers that Eskenazi reviewed removed between 3 standard deviations, so data points that are either 3 or 2.5 standard deviations above the overall mean, right? They can. Overall mean, there may be more slower conditions. Yeah, no, the overall mean in each of the conditions, obviously, yes, above the mean in each condition. I mean, yes, of course. So this is what you may find in your field, but again, obviously check that this also applies to you. Maybe this is not even often done, or maybe it is done, but the number is different, right? And I'll just pass to Agnieszka for data.
Yes.
I think we are halfway through, so that's good.
Yes, the exciting part, apparently. Yes, so once we've done everything that we have talked about, defined our areas of interest, the cleaning and all sorts of things, we are ready for exports. And we need to know what we want to export because there are very many different options. So each eye tracking system has different types of reports, and I'm listing here on this slide the different types of reports that are available in iLink. So trial report, Valentina already mentioned when you want to look into the tracking ratio, interest area report. So this will show you, I'll be showing this, it will show you data per area of interest, fixation report with fixation level data, or the same with Saccad. Sample is like the most detailed one. And you can also have messages reports if you inserted some messages, if there's like some clicks, or so we haven't used messages that much, but there is an option there to do that. And I have all my exciting slides here. Not very exciting. Yes. Okay. So what I'm showing here, this is from iLink. So on the left-hand side, you see a window. So this is what all the exports look like. So we have a window. This is trial output. And on the left-hand side here in this window, you have all the different metrics, all the different options available to you, what you want to export. Once you decide which ones you want, you put them to the window on the right, and this you click the arrow here, you can add them, and then this arrow to the left, we can remove them, put them back, and then you can arrange up and down which ones do you want to come first, right? If the list is long, so these arrows, you would just move this, so that in Excel later you have these columns first, essentially. The problem is, of course, that these are names. Some of them are quite cryptic and not very easily understandable. So all this needs to be done with, you know, the definitions of these metrics. And if you don't know what you're doing, well, you need to read them anyway. Yeah, but that's the thing. And different manufacturers, as we said, use different names. So in the manual, that's the second screenshot on the right, you have this long table. It's just the beginning of table. It's very long. You have all the metrics available in this type of report and their explanations. And the whole take-home message I want to convey here really is that different reports allow you to export different metrics. Okay, that's the key thing. So depending on what you want, you'll get this. So once you do your export, you can open in Excel, whatever software. This is what it will look like. This is the trial report. In this particular experiment, we had 3 trials, so they watched 3 videos. So you have data from per participant per trial. So one row of data would be 1 trial per participant. So we have 3 rows for participant 1, 3 rows for participant 2, etc. Okay, and you have all the different information here. For instance, percentage of missing data, right? Blink duration. This is what it looks like. Okay, this is the kind of level of detail. Well, if you're interested in blinks, we basically use the duration and blink count or blink duration to calculate missing data percentage. Yeah, so we use these to calculate the percentage of missing data essentially. Okay, this is more interesting. This is the interest area report. So depending on what your interest areas are, for us, these are subtitles. For the baby, could be the baby and the nappy, etc. Okay, so you have information here grouped per area of interest, and you can see IA interest area. This is the what iLink calls it. So you've got the definitions. Oops, and this is what the data export will look like. So here we have data only for the first participant, okay, and we have interest area ID. These are the numbers of particular words in the subtitle. So 1 stands for 1, or 10 for the first subtitle, then number 2 stands for the second subtitle, and here interest area label. These are interest area on words. So this is all done automatically, as I said earlier, and you have information, you know, how long this subtitle lasted. So you know, all the dwell time and first fixation duration, fixation count, etc. Okay, so this is 1 row of data is 1 interest area per participant. Okay, so you can see it's much more detailed than the previous one where we had the entire trial per participant, right? So here is 1 word. Yeah, fixation report is even more detailed, right? Because what you have is you have 1 fixation per row. So this is what it looks like. Okay, so lots of data. So this one has much more data than the previous one, right? And so we have information about every fixation that was there. And of course, there's information which area of interest it was on, etc. But this is this one you would use to calculate mean fixation duration, for instance. Sorry. Yes. And the same with Saccard report and, you know, all sorts of things. The reason I'm mentioning this is that we're getting those questions very often. How many participants should I test in my study? So it sort of depends on the level of detail and kind of data and metrics you are going to analyze. Maybe I'll return to this issue in a moment. Yes, and similarly in SMI, yes, Aga?
Does it take long to export the data?
Yes.
It depends
Several.
it depends on the trial.
Those things outside your interest area to speed up the change, have less data, no?
Yes, but it does take several hours.
I
We-
think
so we-
it depends on the report, right?
Yeah.
So some reports are, so in interest area reports, because you have one report, one line per interest area, as Agnieszka said. So the program has to aggregate all the individual fixations on the words we are concerned. Yeah, yes, right. So this will take, this is the one that takes the longest. And sometimes we have to leave it overnight. And obviously this will depend by how many videos you have per participant. Typically for us, it takes a long time.
overnight, one report.
Yes, yes. So generally an interest area report is overnight. So we leave it there and then we go the next day and the report is done. You may also find that if you collect data from too many people, Excel doesn't have enough rows. This has happened to me, and Excel actually has a finite number of.
For example, but I was doing a pupillometry study, right? But you cannot do it in Excel. I actually had to find a special function in R to actually aggregate all the data.
Yeah,
and divide
that's
it
what
by
we did as well. Yeah, yeah. So
you can
then
export-
what you can do actually maybe we can
Export per
we
participant,
yes.
for instance.
Yeah.
Is it
So
here? Yeah.
You can have a report per participant.
Create one report per EDF file. I mean, this is quite small. So the EDF file, you have one EDF file per participant. So you do these, and then exactly as you said, I'm just repeating for the people at home because you cannot generally hear. And then you can just stitch together because the data will be the same, right? So you just append one after the other, and then you will have your data set. But so yes, thanks for the question because it's quite interesting. Sometimes they are very, very big data sets.
Yes. Okay, SMI, the same logic, different types of reports. Okay, so for raw data, where if you're interested in pupil dilation, so you'd go for the raw data export here. If you're interested in events, event is a fixation, Saccard or blink in SMI's terminology. So information about all those things, you'd go for events reports. Also, we haven't mentioned that yet. You may show participants certain stimuli and ask them questions. So both SMI and iLink allow the insertion of these questions within the experiment, and then obviously, I don't know, comprehension questions, for instance, right? And then there is a separate export in SMI for the questionnaire data. If you're interested in fixations in areas of interest in SMI, there's a report that's called AOI fixations. It can do some summary statistics for you. So interest area report, again, aggregated data on the whole area of interest. And here, detailed statistics is per area of interest per participant. So this is what we used to do. Hui Huang, if you're watching this now, this is what you did as well. So we have one row of data per participant per area of interest. So that's participant 1. And area of interest would be subtitle here, number 60. Okay, so it's sort of depending on what kind of report you're using and metrics you're using, you'll have more or less data. So if you're using aggregated reports, am I going to talk about this now, or do we have some?
I'll start the data
Okay,
analysis.
so I'll be back in a moment.
Okay. Wait, if you want to finish your sentence, go ahead.
No, it's
Okay. Okay. Well, we'll move to data analysis now.
There's a suspense there.
Yes. Yeah. So, I will be quite brief, but I do want to point out and start for some quotes about pre-processing the data. So now we're talking about, we have exported the data, we have these data sets, and we are ready to analyze. Well, actually 80% of data analysis time is spent on cleaning and preparing the data. This is something that I personally suffered quite a lot from, and I thought, why am I not even you know, where is the correlation? Where is the t-test? Where is the linear regression? You know, I am miles away from that. And it took a long time to process the data. Well, this is normal. There is a huge amount of effort spent cleaning data. And oftentimes you will have to repeat this over and over again during the course of the analysis as new problems come to light, as Adli Wickham said, or also as you change the type of analysis that you need to do. So,
Philips mal Alman.
can we, sorry, you guys have, someone has their microphone not muted. Please mute your microphone.
Unless you want to ask a question, but.
I think they did not want, otherwise they would have done
Yeah.
so. Okay, so so new problems might come to light, or you run a different analysis, right? So as Agnieszka will talk about ANOVAs and linear mixed models, they require the data to be in different formats, right? So this is, for example, a reason why we will have to do this. So let's look at some of these pre-processing steps. In iLink, in previous sessions, we mentioned you can record data binocularly. If you do so, you have data for the left eye and data for the right eye. And when you export the data, either fixation report or interest area reports, these eye data sets will be separate. So if, for example, you see that a participant has, you collect data binocularly, a participant has a really important issue, but only on the right eye, so you decide to use the left eye just for that participant, because in their left eye, they have no eye conditions and the data is looking good after you've carried out your data quality checks, then you're going to have to merge this, right? So this is one thing that is going to happen. You also need to merge eye tracking data with participant demographics, age, education, gender, for example. Sometimes you can add this stuff already at the design stage in iLink. We have our own procedures to quite quickly do this outside. So we generally have a demographics questionnaire. So we have the data there and then we merge. You might want to merge in item information, so subtitle words. So we typically, for example, when we are dealing with words, even in normal text processing, you may want to add things like word frequency, word length, word predictability, word concreteness values, this kind of information. Or when we talk about subtitles, we might want to know where this word was in a subtitle that has one line or two lines, because two lines imply return sweeps and other types of eye movements that you want to be aware of, and where on the line the word was appearing, in the middle, at the beginning, or at the end.
What you're talking about now is playing around with the data index rather than
Yes.
Yeah, so I mean, not really playing around. So like you create your data set where you have all your words, right? And for these words, you extract variables like fixation, etc. And then you have this separate word, a separate small data set just with item level information. And then you merge this to the huge data set that has perhaps just word number, right? And then you use the word number to match the data from one data set to the other. You merge them. We do this in R generally. I think it's a bit really error prone if you were to do that in Excel, but I'm sure you can. And then you can also add data from other tests that you may want participants to perform in your own software. So for example, working memory tests. We use a company called Milliseconds that produces the software called Inquisit. So this happens outside of the eye tracking data. And then we want to add this to each. So we have these participant codes, PO1, PO2, and each of these has in a separate data set information about their working memory capacity, their results in a learning test or in a comprehension test. So this also is part of pre-processing. You're going to have to add this to whatever comes out of the eye tracking software. And then sometimes, not always, but you may want to integrate data from other programs like key logging software, EDA, electrodermal activity, or EEG, or fMRI, and this has its own processing requirements, right, that you will need to take into account. And you also have to make sure that the data is tidy, which means, for example, that there are no artifact fixations in there, artifact rows, sorry, there are no missing data rows that you have to ask yourself why, or no crazy high, values that might have come from a data entry error or something like this. So, and importantly, that the data is in the right format. So long, what is called long, I'm not going to explain, but just going to point you towards it, look it up. Long format is needed for things like regression analysis, and short format is needed for things like ANOVA, where the information is already aggregated. And
White.
sorry, white and long, yes. What did I say? Short. So data analysis is likely to then, once you get to it, once you have pre-processed the data, is likely to involve statistical analysis software. So we generally don't analyze the data within the eye tracking software. This is important because in iLink, I'm not sure even if this is possible, but certainly in Tobii, and I think in SMI as well, you have some possible statistics that you can already run inside the eye tracking software. We tend to not do that. We just do all our statistical analysis in R, and then there you have other software, SPSS, Stata, Python, or SAS. It is pretty good or I would say necessary to know, or at least have a pretty good idea what statistical test you want to perform, right? Because this is related to a number of things, data types, and also the reports that you get out of the eye tracking software. So do you use a fixation report or do you use an interest area report? This depends, right, on the type of test that you want to run. And also part of it is going to be due to the type of data. This is in part dictating what kind of analysis you will need to use. Continuous data is basically numerical data, to simplify it. Categorical data is what we call factors, and it's just, so items that have so variables that have a number of levels. For example, nativeness. So you then use native English speakers and non-native English speakers. Then your category would be language, and then you would have. Yes, or speed, like in our case, we run quite a lot of studies with subtitle speed, and in the latest one, we have 3 speeds. So we have a variable with 3 levels, right? It's a categorical variable with 3 levels, or the data can be dichotomous. In terms of the eye tracking data, for example, skipping is generally dichotomous. So for each word, you will have a 0 or a 1 value. So only 2 values can be taken by this variable. 0 means that that the word was not skipped, so it was fixated in first pass reading, and 1 is the opposite. 1 means the word was not fixated, was skipped, right? Or a comprehension test as well. You could just aggregate, right, and have like if you give your participant 10 questions about comprehension, then you could have 1 average accuracy score for that participant, or you could have 10 rows of data for that participant in which each question has a yes or no, correct or incorrect, right? This is also dichotomous data. So this kind of the type of data that you are dealing with will dictate to some extent what type of analysis you're going to run. And then all the usual suspects, do run your descriptive statistics, measures of frequency, central tendency, and dispersion. I'm not going to explain what they are. I'm just going to say that they are necessary, and that's what they do generally. As soon as we get these data sets, we explore the data sets, right? We check for normality. You can use this by using specific tests like the Shapiro-Wilk test. You can also check for skewness or kurtosis of your data. And then plotting, right? Histograms, box plots, sometimes line graphs, PP plots, QQ plots. So this is again for normality. And then of course, calculate your means and medians, right? So this is pretty basic stuff. And obviously, as I mentioned here, histograms, box plots, that's data visualization. And I just really want to say quickly, explore your data visually. This is this is a key part of data analysis, and really a picture is worth 1,000 words. You may recognize this, the author of this quote, John Tukey, who is a statistician, who really sort of captures the importance of visualizing data. So I'll stop here and I'll pass the word to Agnieszka to talk about ANOVA and mixed effect models.
How exciting is this? Okay, this will be mainly related to the history of how we did things, or I did things, because you started with mixed models already, didn't you? Yeah, so in the old days, people would do simpler tests, ANOVAs and t-tests, and now the trend is to look into more detailed analysis, more powerful analysis, such as mixed models. And I would like to show you what it looked like on eye tracking data. So if you're doing a t-test for 2 groups of participants, or ANOVA, we have at least 3, let's say, put it simply, what you're interested in is a mean value per participant. So your data set looks like this, okay? So I have 1 row per participant. These values are made up values, by the way, for mean fixation duration. So we had 2 conditions. Participants watched 2 clips, one with slow subtitles and one with fast subtitles. So it's like for a t-test really here. And you have participant 1, this condition, and the other condition, participant 2, participant 3, etc. Okay, so 1 row of data. So this is data that is aggregated. So we took all the words in all the subtitles in this clip, and we ended up with 1 number. Okay, this is what we used to do. I'm sorry to say, but this is what it looks like. Okay, so going back to this question, how many participants do I need? So if you're doing this, you obviously need more participants because you don't have very many data points here, because you've reduced all the possible data points that you can have into a single number per condition per participant. So we typically say, I don't know, at least 30, 40 per condition in terms of participants for ANOVA, because you have to get rid of some of the data anyway, because it's not good for quality reasons. Okay, so this is what an aggregated test looks like. And if you think about that, I mean, maybe in some studies, in some tests, depends what you're doing. It's enough. It's okay to have this 1 value, but in reading studies, particularly with reading subtitles, what we are doing is we are really disregarding the variation that we have between different words. And as we said previously, the word length, the word frequency, concreteness, all those values do matter, okay? We also disregard variation within the subtitle itself. So we can have a subtitle that consists of 1 single word in a single line, or we can have a 2-line subtitle with very many difficult words, etc. And what we ended up with here in ANOVA was 1 single value. So we're actually throwing out a lot of data and not using it, okay? So the solution to those problems would be to use mixed models, and these well, powerful statistical tools, let's say, allow us to analyze data. And when you think about that, previous like traditional tests require very often the data to be independent. And when you have data in eye tracking from participants, when you look into mean fixation duration, for instance, right? So you have thousands of fixations from 1 participant. So the fixations are not really independent, right? Because they come from 1 participant. And there's a lot of variation, in particular in mean fixation duration between different participants. So it's not accounted for in an ANOVA because we average it out, so we lose the data, but it can be accounted for in mixed models, especially if we have some repeated measures designs, right? And obviously, the data that we have, be it, I don't know, comprehension or data coming from the reading of subtitles, will be different for different participants, right? So 1 participant will, I don't know, if they're reading in English, Polish participants, they will know English better, so they will have different reading patterns for all the subtitles versus somebody who doesn't know English that well. So for an ANOVA, you'd have to create like a different category, right? For this, you'd have to, I don't know, say beginners, intermediate, advanced learners, etc. Okay. For mixed models, what you can do, you can give them a test, and we've been using several tests recommended by Agnieszka, for instance, like the even Cambridge Proficiency or Lexdale or whatever, and you get a number per participant and you include that in a model. You don't need to create additional factors for this analysis. So much more powerful. And what's the difference in terms of the data points? Let me go back to this in a moment. So this is, we're comparing this to the ANOVA t-test data set, right? So this is the kind of data that you can have when you're doing mixed models. And for mixed models, I think it's like at least 1,600 data points to be able to run the mixed model. So you need, I mean, There are not that many that's what the recommendation is, right? But depending on what kind of export you're doing here, what I'm showing is I'm showing one. This is an interest area report, so to speak. So I'll have one data row per participant per subtitle. And I also here included the speed, also what type of clip. So there were different videos. So what kind of video it was, whether that's the number of the subtitle here, whether it was a one-liner or two-liner, and then fixation count, word count in this particular subtitle. So I have subtitle level data, and then the mean fixation duration that I'm studying. Again, this is aggregated because it's per subtitle here. You can have it per word, or as I said earlier, you can have one fixation per row, which would be great in terms of having many more data points to make your analyses more powerful. So for just to sum up, right? So for the t-test or for an ANOVA, you'd have the same number of rows per participants. So not much you can do there. For mixed models, again, depending on your research question, you can have one word per subtitle per area of interest. Is it the timing? No, it's like timing. Yeah. We're making an effort not to talk for too long, right? Or even one word per fixation, as I said, and mixed models are great. You can incorporate this. Yes, the problems with aggregating data, I think I already explained. So basically, you disregard all the variation that is there in subtitles, in words, and mixed models allow you to, well, not to do that, right? And they also allow you to explain the variance that normally is related to differences between participants or the different words, and then also increase the power of your analysis. And I think that's it for me. No? MFD values are highly correlated. I already mentioned that. And
okay, so I can take over. So when we run mixed effect models, so thank you, Agnieszka, for giving us that introduction, we generally talk, why are these models called mixed, right? They are mixed because we use a mix of fixed effect, so-called, and random effects. What are these things? Okay, so this is not a stats class, but this is where we try to sort of explain in non-statistical terms and a bit more understandable terms. So fixed effects are basically the variables of interest to us, right? So for example, if we want to know whether speed affects reading patterns, then speed will be a primary variable of interest to us. They're also called independent variables, predictor variables, explanatory variables. You may see them described with different words, right? So subtitle speed is one example. Cognateness, for example, if we are interested in whether cognates are recognized faster, or if we are interested in differences in reading patterns between native speakers and non-native speakers of a given language, then that was going to be a really crucial element for us. It's going to be a fixed effect in our model. They can be entered as factor or covariates, right? Depending on whether they are of primary or secondary interest. So primary interest would be these examples that I've just given you. And then secondary interest, so covariates would be things that we know matter, but are not in our sort of main research question. For example, if we're interested in whether native speakers different from non-native speakers in terms of processing subtitles, we know that subtitles are made of words, and we know that word length, for example, has its own independent and quite stable and quite large effect on fixations. And so we might want to control for this, because how long anyone, regardless of the first language, is going to spend on a word is partially at least due to how long this word is, or the probability of skipping. If a word is really short, it might be more likely to be skipped. So all of these, so word length could be entered as a covariate in the model, right? So it will be a fixed effect, right? But it can be our primary or secondary in terms of our main interest and research questions. Some quotes, this is a particularly cryptic one. Unknown constant parameters associated with yes, these definitions, right? Unknown constant parameters associated with either continuous covariates or the levels of categorical factors in an LMM, linear mixed model. What this means is just a fancy and pretty unclear, in my opinion, way of saying that these variables can either be continuous, so it can be numerical, or they can be categorical, right? So we can ask, for example, if age has an effect on reading, right? Do people read differently when they're really old than versus when they're really, really young? And this would be a numerical variable. Or we can ask whether cognateness, so the status of being a cognate or non-cognate, so this would be a categorical variable, right? Other quote, in my opinion, perhaps it would be better, the typical way to compare differences between treatments or the effect of continuous predictor variables. That's another way of defining what a fixed effect is. Okay, when it comes to random effects, on the other hand, these are, as Agnieszka already pointed to earlier, these are sources of random variation, right? So let's try to unpack that a little bit. Another quote by West, unobserved random variables, unobserved because we are not going there to collect these variables, right? They just occur naturally within our data. This is the sources of noise, right? And they are usually assumed to follow a normal distribution. So actually your dependent variable doesn't have to be normally distributed, but the random effects need to be. Okay, so this is one thing to be aware of. They have also been defined as experimental or observational blocks within which you have several observations. This is, however, more applicable to things like biology or even education, where you have different pupils in different schools and different classrooms, right? And this information is not something that you're particularly interested in, but it may introduce variation, systematic variation that might mess up your data. So you want to account for that, right? I like Winter's definition. Here, the primary, so a random effect is the primary workhorse for dealing with clusters or non-independent data points, right? And this can be, these random effects can be divided in random intercepts and random slopes. More about that in a second. Now, the important bit here is clusters or non-independent data points. So if, as Agnieszka already mentioned, actually, if there are multiple data points on the same item or from the same participant, so if I am participant one, we collect data on, a clip that is 5 minutes long and there are 100 subtitles in there, the same participant will look and provide their eye movements for each of these subtitles, right? So we'll have 100 subtitle level data points for this participant. Well, some participants are faster than others, aren't they? Or slower, right? And this may have nothing to do with your actual hypothesis and with your research question, that is, let's say, cognates are read faster, right? So this may introduce natural variation that is basically noise, right? That is totally unaccounted for and just sort of boxed and labeled as noise, as error in the models, unexplained variance, right? Well, the powerful aspect of linear mixed models is that you can take this noise, this variation, and put it in the model. So it is of interest to us, and we account for it via entering it not as a fixed effect, so as our main variable of interest, but as these random effects, and we give structure. We allow the models to look at if there is any structure in this variation, okay? So whilst fixed effects can be continuous or categorical, as that cryptic quote by West was trying to tell us earlier, random effects must be necessarily categorical, right? So even if you have hundreds of categories, they remain categories, right? They are not numbers. So subtitle one, so if this type of subtitle can be, number of subtitles can be a source of random variation, because there is natural variation within the subtitles. The words in there are different, right? Even if you have 100 subtitles, this will not be entered as a number. You need to turn this into a category. So label 1, label 2, label 3, okay, but these are labels, they are not numbers. Fixed effects are also assumed to be constant across experiments. This means that they can be repeated, right? Okay, so which means that whilst individual participants will vary, right? And these individual participants from experiment to experiment, I mean, so when you collect more data, you will use different people, right? And this is your source of random influence, random variation in the data. But if you're interested in looking at gender effects or speed or cognateness, this, which is a fixed effect, you can test again and again and again with new samples of participants, right? So typical fixed effects in psychology are participants and items. And as I mentioned, subtitles for, what did I say? Okay, random effects, yes, of course. Random effects is participants and items, right? So these are the things that will change, that will introduce random variation, and you want to control for that. An item by item here, we can mean anything from visual stimuli in a picture naming study to sentences or to sentence words, right? The different words that you use, these may have particular idiosyncratic properties that will mess up with your data, even if they are all cognates, right? So you use these as a random effects that you control for in your models. Now, we said earlier that random effects are really generally divided into random intercepts and random slopes. Now, what does this mean? So what I'm going to try to do next, and this is my kind of last slide, really that is a bit hefty, is to give you an explanation that is simple and completely devoid of any mathematical elements. So there won't be any equations in here. We're going to use visualizations, right, to explain what's an intercept and what's a slope. So let's just look at what we are actually seeing on this screen. So in each of these panels, you see people, right? So these represent people. There is a black solid line, which is in exactly the same place. The black solid line is the model prediction of the average overall effect across all participants, right? Modeling typically tries to linear mixed effect models, they are called. The hint is in the name. What these models try to do is to fit a line that goes through your data, right? And this line is supposed to approximate, so you try to find the line of best fit, so-called, to best approximate where the data is. Now, well, so this black line is the approximation given all of the participants, okay? So where the model thinks that the overall mean is. And then you have the dashed line, which is participant-specific estimates, right? And you have the circles, which are the actual data points. So this is what, you know, the actual fixations that each participant makes. These are the circles, right? And then you have these dashed lines, which try to go through the data, right, to approximate it. Now, and then you have on the x-axis, you have what is called trial order. So this is experimental time, right? So if your experiment is 1 hour long and you have 3 trials, like what happens as time passes, right? And then on the vertical axis, which is the y-axis, you have response time. How long does it take to the participant to recognize that the word is a word in the English language? In cases when this is a cognate versus a non-cognate, okay? Let's suppose that this is our experimental setting here. Then on the top row, right, so the first 3 panels, we're looking at random intercepts only. This is crucial, please have a look. And at the bottom, you have random intercepts and random slopes, okay? So this is just, and I will be talking about both. Now, what we can see, if we now examine the circles, especially in the top panel first, is we can see that what happens as time goes, right? These circles, if we now look at the vertical axis, are going in this direction. So this means that both Yasmin and Logan are getting faster. So as time goes, their response time decreases. They're getting faster. And this is quite typical. It's called learning effect or test effects. You know, if I'm shown 150 words, and some of them are cognates, some of them are non-cognates, some of them are foils, and I need to recognize and say whether they are a part of the English language or not, and I press a button, I might become faster as I repeat this process many, many times. However, if you look at Dan, who is on the last panel on the top, if I can here, right? What we see for Dan, so here we can see that the data points, you know, the line is with different angles perhaps, but it's going down. With Dan, it seems to be doing the exact opposite, right? So if we were trying to find a line of best fit, it certainly wouldn't be that dashed line. It would be something like that, right? So what this means is that Dan, unlike Yasmin and Logan, is actually getting slower, perhaps due to fatigue. He didn't sleep last night, he came in and did your experiment and he's about to fall asleep, so he's getting slower, okay? So actually, when we look at these dashed lines, the dashed line, which is this line of best fit, allegedly, that the model is trying to estimate, for Yasmin, this is quite okay, right? It goes through more or less all the data points. For Logan, we are here in this case, the data, I mean, these data points here and these data points here are not really accounted for properly, but at least the direction is kind of captured, but not really precisely, right? And for Dan, this dashed line is not representative of his data points at all, right? So, and this is because on the top rows, we only allow the intercepts to change. So what is an intercept? The intercepts in terms of the visual representation of the data is nothing but where your prediction line hits the y-axis, right? Hits the vertical axis. So you can see that in one case, in Yasmin's case is here, in Logan's case is much closer to the line of overall fit, and in Dan's case is above, right? But what is key is that these dashed lines are always parallel to the black line. So they will change in where they hit the vertical axis, but their angle is not allowed to change. So this is a situation in which we fit a random intercept, right? For trial, random intercept. Now, if we move to the bottom part of the graph, we have random intercepts. So we see that these dashed lines, so the prediction, are still hitting the vertical axis at different heights, right? But what we see is also the angle of these lines is allowed to change. And this allows us to capture the variability between these participants, some of which naturally get faster, some others get slower, right, more precisely. So the line of best fit for Yasmin, it's not very different between the two panels, right, top and bottom. For Logan, it is quite different because now that we can change the angle of this line, we can better capture the top and the bottom set of data points, so those circles that are here and here, right? And perhaps the highest improvement we can see in Dan, right? So now the line of best fit is actually managing to capture the variation in this participant. So this is the difference. So intercepts are nothing but where on the height in the vertical axis at which your prediction line hits intercepts, right? That's why they're called intercepts, the vertical axis, and the slope is nothing but the angle at which this line is, right? And at the bottom, and what we're doing here, and this will be my last sort of words about this, is that what we are doing in the bottom, where we fit random intercepts and slopes, the sort of right terminology here is that we are fitting a bi-participant slope. Here, I'm only talking about participants. You can do exactly the same things for items, okay? Parentheses closed. So you are fitting a bi-participant slope for trial order. In other words, we are allowing trial order, so the effect of this time that this time has on response time, to vary by participant. Okay, and this can be very powerful because it allows us to capture this variability, to use it to explain variance in the models. And then if you find still, once you have controlled for all of this, that your cognateness, so your hypothesized effect is still there, then you can see that this is powerful. So despite this random variation that in things like ANOVAs is totally disregarded, right? Despite this having been accounted for, cognateness is still significant, let's say, still has an effect, right? So I hope that this is a sort of clear-ish explanation of at least visually what random intercepts and slopes are. Here you have another example, you know, of a more colorful graph. Which Agnieszka produced with our colleague Breno. So on the left-hand side, we see, so the blue line, the one that doesn't have any blue data points, is our overall prediction, right? And then all of the other lines that have data points associated with them are the predictions for each individual participants. And as we can see, they're all parallel, right? So they will hit the mean fixation duration, so the y-axis, the vertical axis, they will hit it at different points, here, here, here.
Yeah, that means actually, right, that for some participants, mean fixation duration on average is smaller, and for others it will be larger.
Absolutely, yes.
So that's what it means.
Yes,
really.
and in the random intercept and random slopes, we can see that the angle of this line is also different, okay? So that's kind of all. So take-home messages for today, and then we are really about to finish, and that is amazing because we have quite a lot of time for questions, is the following. So in short, please make sure you inspect your data visually, both before you run any models, so at the sort of the descriptive stage, right? And when you run models, we've looked at some of these graphs just now. Follow a clear data quality procedure. So, I mean, we've kind of explained how we do it in iLink. This will depend on which system you use, right? So if you use Toby, maybe you want to use these sampling rates. In iLink, it will be a multi-step procedure. Apply appropriate data cleaning. So fixation, trimming, fixation, cleaning for the most part, so trimming, outlier removal, and all of this. And remember that you will have to do this even if your data is of perfect quality. This is just a standard step, and you have to check your field for what the sort of what is done usually, and know what data analysis you want to perform before you actually export your data. Simply because sometimes the data analysis will determine whether you need an interest area report or a fixation report. And because it takes quite long, as we have said earlier, to actually export these reports, it's advisable that you have a clear idea beforehand. And always make notes about what you do and the rationale for your choices. So as you've probably gathered by now, I mean, there's lots of thresholds, lots of decisions that you need to make at all points.
Which you forget when you write the paper.
And yes, so what we started doing, I think it will work really well. Only realized this on the 4th experiment that we're running. But so when you do this, already have a draft of your paper and the methodology section and just jot it all down, right? And will be much more precise maybe than what you need. And you might end up not including this or including it in the appendix, but it saves you a lot of hassle when you then 2 months later you're deep in data analysis, and then you have to write a paper and you're thinking, oh, what did we do there again? What was the threshold? You know, so this is just sort of hands-on advice on how to proceed, and always refer to best practices in your field. I hope I have shown you appropriately that it is often a judgment call. So try to read quite a lot, because this is the only way in which you start forming an idea of what actually is done in the majority of cases. And we've provided quite a lot of resources. So if you check the bibliography here, you'll be able to go and look at some of these best practices, at least in psycholinguistics and psycholanguage acquisition. Talking about best practices, there's this pre-print paper that has come out recently. I think this was you added this. And they had a list of things. Also, I would suggest looking at Carter and Luke, or looking at this Eskenazi review that we showed earlier. And actually, all of the books, we always have this slide at the end of all our presentation, all of these books also are pretty good places where you can have an idea about best practice operations in your field. So I think this is all from us.
Yeah, you had
oh yeah, this is just
no, that's what I meant, right? So the long list
of bibliography, yes.
Yeah,
so
just
this is
share it, and then you can go to YouTube and just pause to note it down
and type it out.
Okay, sorry, going back. Our next meeting.
Yes, so we are meeting on the 22nd of February. Room and time are on the screen. If you are,
We are meeting in the eye tracking lab downstairs. In
So we don't need a room for this.
no, yes, because the eye tracker
no,
is
we
yeah.
booked it
Because we
already.
already have a room booked for other
Yeah.
research hub meetings, right?
Yes. So what's going to happen in term 2? We're going to have 4 sessions, right? 2 on SMI to get started. It's an easier system, and then 2 on iLink. Okay.
So I think it's February, March, and then April and May. So you're going to lead the SMI ones in April, February and March, and then April and May I'll be leading the ones on
Yes,
iLink.
and this will not be recorded, and this will not be on Zoom. Sorry.
Well, we at least hope that the theoretical parts, of which this is the last sort of installment, have been useful. They certainly have been very enjoyable for us. I don't want to talk for you, but I enjoyed it. And we are now ready to take some questions.
Yes, shall we perhaps?
Oh, there might be something on the chat. Okay.
No, Hui Huang, yes, he commented on something. We didn't see the chat before, so we'll stop sharing. Are there any questions on Zoom or in the room?
One more. Because with the line of the method, you said the either can include this flow or not. So what are the advantages of not including?
That's a very good question. There are definitely some advantages in not including it, and that is, for example, if you don't have enough data points. So adding random slopes and random intercepts takes away degrees of freedom from your model. Now, I'm not, don't, you know, as I said, this is not a statistics class, but you need a lot of data, right? If you don't have this data, so we also apply something called a modeling process. So we try to fit, models with different random effect structures, right? So you might be able to fit only one slope, but you may have 3 main predictor variables, 3 fixed effects, right? Or you may be able to not fit any, right? So this depends. So one of the advantages of not fitting slopes is that your models at least will be fitted. So you will get a model, right? If you don't have enough data, of course, you know, in an ideal world, you will have enough data, and so you will try to fit as many slopes as possible. However, another thing you do is often you compare models. You use ANOVA, right? Is used actually as part of the modeling process to compare models with different structures, right? And so it's possible that you add this random slope, but actually if we don't have that variation, right? So we remember when maybe we can keep sharing the screen.
Yeah, maybe.
So if you don't have that variation that we could see, let me see if I can manage to get there. So we could see Dan here, right? Dan was acting very differently from the other participants. So, but if that is not there, so then maybe the slope is not necessary. It's not, I mean, from what because I've used it to describe why random slopes are good, right? That I wouldn't want you to be misled into thinking that they are always a good thing and that we always need to fit them, right? There is something called a parsimonious model, which is this, you know, try to fit the simplest model that is appropriate to the number of data points that you have, and be aware that if you have many conditions of interest, this exponentially increases the number of data points that you need to have, right? So if you only are interested in, I don't know, native language and cognateness, right? Because we've been talking about that. And then you for example, you want to see if the two things are not correlate, another word is not interact, right? If there is an interaction, that's already 3 things, right? And you need a lot of data points for this. At the moment you're interested in adding covariates like fixation, like frequency or word length and all of this will take degrees of freedom. So you may not simply have enough.
Yeah, for us, what happens, we don't fit slope. Well, models just don't fit essentially when we add slopes.
It depends. Sometimes they do, and we try. Yes, we definitely try. And sometimes, you know, the model of best fit, which you compare and look at, does have at least one slope, maybe only in the by subject. Because I remember I told you you can also add it in the by item, right? You can have by item slopes, right? So so yeah, sometimes the model best fit doesn't have even any slopes. Yeah, so it could be advantageous not to have them, but always try to test for them.
It's better if you can keep them, if not, then
generally at least random intercepts, right? Because if you don't have any random intercepts and you don't have any random slopes, then you don't have any random effects. So why are you using mixed model in the first place, right? Maybe you can just go to the ordinary linear regression, but generally at least a minimal intercept is fitted, and then we try to see if any slopes are worth fitting and if they improve model fit or not. Thank you, that was a really good question. Anything else? Maybe from anyone at home, if you would like to ask a question, please just unmute yourself and ask away.
Yes, I do have a question on scheming. Because from my first experiment on speed, the comprehension is no significant, but the character identification and subtitle recognition are significant to me, which means the faster subtitles means produced. Let me take a look 1 second.
So you use the character identification and comprehension, and what else?
And also subtitle recognition. So which means participants can generally manage fast subtitle speed as sufficient for grasping the basic gist through reading the subtitles while watching the screen. But the nuance, fast speed adversely affected the ability to notice, observe, and recall specific details such as nuanced visual information, which
How do
means
you know that? Did you have a test for visual? Like
That was in character recognition, I think.
yeah,
oh, so character, not like a Chinese character, but characters like as the person. Okay, sorry, yes.
and
What's
also
your question, Hui Huang?
I mean, I cannot quantify the frequency of the subtitle skipping. And you mentioned a 0, 1 before, right? 0 means no skipping, and 1 means skipping. So I mean, can we quantify the frequency of subtitle? So I mean, which are skimming.
Skipped. Yeah. So can I ask you a few things? The first one is, are you using iLink?
No, I'm using an SMI.
Okay, so I probably don't know the answer to. So this 0 and 1 is only in iLink. In iLink, we have a variable that you can export in these reports that that Agnieszka showed earlier, right? Oh, okay. Well, I can't. So in these reports that Agnieszka showed earlier, you can extract variables, and one of these variables is called interest area skipped, and it's a measure of skipping in first pass reading, right? Which means that and you have these dichotomous variables 0 and 1, but I don't know if this is available in
I
SMI.
think, when you were here in Warsaw, we exported the percentages of subtitles skipped, which is in one of the aggregated reports. So you do have a measure, so you can compare for the slow and the fast subtitles, the percentage of skipped subtitles, right? You have
Yeah.
this, yeah? So it is, you can quantify it, yes.
So it will be quantified in a different way. So you will not use this as a sort of dichotomous variable, but you will have a percentage instead.
Yeah, but you can do dichotomous as well. If you look at fixations, if there was a fixation on a word, that means it was fixated. And if there wasn't, that means it wasn't fixated, right? So if you don't want to rely on the aggregated data, you can look into more detailed data from another report. So you can definitely do this.
Okay, great. Thank you so much.
Thank you for your question. Any other?
No, I think it was up.
Okay, so, oh yeah, it's 1. So, well, we have to say goodbye. Thank you very much for taking part. Thank you, Hui, for your question. Thank you to Hugh Salari for taking part. And we will see some of you in the practicals, hopefully. So perhaps we can just stop.
The recording, yes.